Okay, I'm going to take a quick walk through problem 4.3. This is the most complicated problem, but not much different than the first problem or the second problem. Just has all the components that were in the others. We have 3 turbines, we have 2 pumps, we have an open feed water heater and a closed feed water heater. And so all these components and a trap between the closed feed water heater and the open feed water heater. So it's got everything that problem 2 had, but we added reheat in here. So just in general, let me just draw 3 turbines. And we find out that the reheat is between turbine 1 and 2. So we see here that a fraction of the flow is diverted at the exit of turbine 1 into a closed feed water heater, while the remainder is reheated to T3 before entering turbine 2. So what we have here is a fraction of this gets diverted to closed feed water heater. This is state 1 coming in, state 2 coming out, and then we have reheat here, and then it goes in at state 3 to turbine 2. Then we come off here. This time we don't have reheat again. If we look where it talks about a fraction being taken off, y double prime after turbine 2, the remainder just enters turbine 3, so no mention of reheat there. So we've got our original steam generator here creating the steam for turbine 1 and then reheat. So we've got 2 places in this power plant, Q for the steam generator and Q for the reheat. And then we have the work out of turbine 1, turbine 2, turbine 3. Of course, we have 2 pumps, we have a condenser, we have an open feed water heater. So there's not too different from the other problems. I don't know that there's any new component that we need to consider. Just include the reheat in our final efficiency equation. Ultimately, what we're going to have is the power for turbine 1, the power for turbine 2, power for turbine 3, minus the power for pump 1, minus the power for pump 2, divided by all the heat transfer that we have to pay for, which would be the Q for the steam generator and the Q for the reheat. And so we find all those terms, of course, like turbine 3, we know it's going to be m dot times 1 minus y prime minus y double prime times our numbering scheme, whatever, so I'll just put H inlet for that turbine minus H exit for turbine 3. The Q for the reheat would be m dot. In that case, at the reheat, we have y prime already taken off, so we've got 1 minus y prime, and it's going to be H exit minus H inlet if we want that to be a positive value. So we find the equation for each term in our entire power plant, and then plug all those into the efficiency equation, and not much different than the previous problems. If you want to start thinking about the project, you might look at the implications of some of the equipment that we've added here. Of course, one obvious thing you might want to consider is, well, what if I reheat again? So I have reheat 2, reheat 1. And maybe, what if I want 2 open feed water heaters? So I'm deviating from the problem, so don't solve the problem for this new design, but if you are wanting to compare that original design, and if I have 2 open feed water heaters, that means that I'm going to have 3 pressures coming back. So right here I have pressure 1 and then a different pressure, pressure 2. Pressure 3 is equal to pressure 2, but another unique pressure is pressure, this is state 4, pressure 4. State 5 would have the same pressure as pressure 4, but then I've got another P6 here coming out. So the unique pressures on the way up, P1, P2, P4, and P6. So coming on the way back up, I'm going to have a pump that brings it from P6 up to P4. And then since the second feed water heater is at another intermediate pressure, I have another pump, P2, that brings it from P4 up to P2. And then I would need another pump that brings it from P2 back to P1. So having the closed feed water heater in the trap allows me to get rid of one of the pumps. So that's another modification. Of course, I have a condenser in here. One other thing is how to number the states. I generally will number them by starting at the steam generator. At the exit of the steam generator, I always label state 1 or going into turbine 1. And then I follow the most direct path through to the condenser and then back to the steam generator. So that would be state 1, 2, 3. This would be state 4 at the exit of turbine 2, state 5 at the inlet of turbine 3, state 6 at the exit, state 7 at the exit of the condenser, state 8, state 9, state 10, 11, and state 12. And then if there's any other paths that I need to consider, then I would, like when there's a trap, add those other states at the end. For this particular power plant, which is not problem 4.3, I've modified this, so just having you in general consider some concepts. Gonna have to add a reheat 2, and I think everything else stayed the same except, well, one more pump. Might want to do a TS diagram of this problem, and I would have 4 pressures. And turbine 1, state 1 to state 2, then it reheats to state 3, drops down, reheats again, drops down to state 6, and then comes out state 7. The pressure gets raised to the next pressure, which is 8, and then the open feed water heater brings it to state 9, and it gets raised to the next pressure, which would be state 10, and then finally in the last pump gets raised to the final pressure, which would be state 12. So 7, 8 in the first pump, then 9 in the feed water heater, 9, 10 in the pump, state 11 in the feed water heater, and then the third pump 11 to 12, and then back. So there's a, again, this is not for homework 4.3, this would be maybe for an idea you have for the project. What I want you to realize is that now that you've worked through 3 problems, you might want to start thinking about, you've seen some of the differences, look at some of the differences in efficiency, and then start thinking about what parameters you want. Like, why did we pick 10% for y prime? Why not 15%? Are there limits to how high y prime could go? Do we always want to make this saturated liquid? Maybe you could, of course, you don't want to go past that. You don't want to get there to be a quality greater than 0, but maybe you want to experiment with not bringing it all the way up to saturated liquid. What happens to the efficiency? These intermediate pressures, P2, P4, why those pressures? Is there an optimal pressure? So these are all questions in the design of a steam power plant that you need to consider, and how they would affect efficiency. And so giving you a little clue on your project, start thinking about that and make sense of these homework problems that you're working on, beyond just, okay, I can do those homework problems, but you should start having a confidence about, I could come up with my own design, I could come up with an initial guess of parameters and then optimize that. And that's in fact what you're going to do with your project. I hope you've enjoyed this homework set. I noticed when I finished that my TS diagram didn't come out so well on the saturated liquid line. So I redrew things. Here's turbine 1, turbine 2, turbine 3 with the 2 reheats. And then on the left side, state 7 is the inlet to my pump, state 8 the exit of the pump, 8 to 9 is the first open feed water heater, and 9 to 10 is the second pump, 10 to 11 the second feed water heater, and then 11 to 12 the third pump, and then finally 12 back to 1 is my boiler. I think that didn't come out very well on the first drawing.